Today I want to talk about Orion, which is a network slicing system that we have designed and implemented, and which targets radio access networks in the context of 5G. And I want to begin by first giving a brief motivation behind the problem. So 5G networks are expected to become multi-service environments, and there you could have various services deployed over a common underlying infrastructure. And these services could have very diverse performance requirements. For example, they could have requirements for high mobility, or a high data rate, or low latency, or a combination of all of these. And the problem is that with conventional mobile network architectures, we cannot deal well with, because it cannot provide multi-service capabilities. And the reason is that conventional architectures follow a one-size-fits-all approach, where basically you have some sophisticated hardware boxes like MMEs or Inode Bs and so on that are interconnected in a fixed topology, and they're generally optimized for the case of mobile broadband. So in this fixed and rigid architecture, it's not very easy to deploy other types of services that might have different requirements. So ideally, what we would like to have is a much more flexible and reconfigurable architecture, and this is the vision behind 5G. And a way to achieve this would be to use a generic underlying infrastructure that could be composed by different wired networks and radio access networks. And then on top of that, to basically deploy isolated logical networks, or as they're called, network slices, each one corresponding to a different service. So these network slices could be composed of a number of virtual network functions like virtual base stations or virtual MMEs and so on, which could be customized, chained together, and deployed over the physical infrastructure based on the requirements of the corresponding service. So obviously, in such a setting, the virtualization of the network functions is something very significant, and this is the main focus of our work, and specifically, how can we enable this virtualization and slicing in the radio access network. So before I proceed presenting our solution, I would first like to give a brief overview of the state of the art in this domain of RAN slicing, where generally we can find solutions that fall into two groups that are in the extreme end of the solution space. So in one end, you have solutions that rely on RAN sharing, and the idea there is that you have a provider who is normally a mobile network operator, that is the owner of the hardware and the spectrum. And then all slices that are deployed on top of it are basically managed by this provider, who has full visibility into their resources and is responsible to control all of their operations, like to schedule their mobile devices, perform mobility management, and so on. And of course, in such an approach, you can have a very efficient and adaptive use of the radio resources, because one entity is responsible to dynamically allocate these resources to every slice as required. But on the other hand, you have no functional isolation among slices, which means that a slice cannot really come in and introduce its own sophisticated control functions. So this is one extreme. And on the other side, we have solutions that rely on what we call full isolation. And the idea there is that each slice gets its own dedicated chunk of hardware and spectrum resources. And then using virtualization techniques like containers or virtual machines, they can deploy their own full protocol stack of a virtual base station, which can be fully customized based on the needs of their service. And in this case, of course, you have functional isolation for slices, because they can be customized as needed. But on the other hand, you no longer have an efficient use of the radio resources, because each slice gets its own dedicated chunk of spectrum, so you no longer have statistical multiplexing gains there. So what we wanted to see in this work is whether we can actually get the good of both worlds and find a middle ground solution to this problem. And based on that, we designed and implemented Orion, which is a RAN slicing system that enables the functional isolation among slices and at the same time allows the efficient utilization of the underlying RAN resources. And to do this and to provide this isolation, among others, Orion introduces a set of abstractions for the virtualization of the radio resources. Now, apart from that, in our paper, we investigate a number of other aspects, but I'm going to focus on the main design of Orion here. So the main idea behind Orion is that we have physical base stations that are basically composed of hardware and spectrum resources, and that are owned by some infrastructure provider. It doesn't have to be a mobile operator. And then all the slices that are deployed over that physical base station basically share a common physical layer, so we assume that they use the same radio access technology. Now, for all of these slices, based on Orion's design, we have separated control and data planes. The data plane of all slices resides at the physical base station. This means the actual traffic that goes through the base station resides there. And then each slice gets its own dedicated virtual control plane, which can be seen as a virtual network function that can be customized by the slice owner in order to introduce sophisticated control operations, like, for example, schedulers or mobility managers that apply to a specific service. And these slices need to communicate with the base station through dedicated channels that can be either logical or physical, depending on the deployment. Now, a problem that we have here, due to the approach that we take in comparison to run sharing and the full isolation, is that in order for these slices, since they share the resources, in order for these slices to be able to operate independently, we need to have some way in which we can reveal these resources to them, and as well as the data plane state, but in full isolation, so that one cannot really have a conflict with the other. So a hypervisor is responsible to do this. This hypervisor sits right in between the physical base station and the control planes of slices, and it is basically responsible to ensure this isolation by, first of all, virtualizing the radio resources, and secondly, virtualizing the data plane state. And I'm going to explain how this is done, starting from the virtualization of the radio resources. So the hypervisor of Orion is responsible to dynamically partition the resources among slices and to distribute these resources based on the slices service level agreements. And these resources are revealed to slices in a virtualized form where the resources not dedicated to a particular slice are omitted. And this would include resources that would be allocated to different slices, but also resources that are going to be used for the random access and broadcast processes, because these are operations that are handled internally by the physical base station. Now, one design choice that we've made in Orion when virtualizing the resources is that we need to abstract the frequency dimension and instead reveal these resources in an abstract indexed-based form. And the reason we do that is because collocated slices might actually belong to competitors, and therefore, if a slice can infer, can actually see the resources in the frequency grid that other slices are using, it could potentially infer things about the operation of those slices and even perform malicious operations that could degrade their performance, like causing interference. So for that reason, we need to have some abstractions that adhere to these constraints, and at the same time, they need to be generic enough so that they can be applicable not just to LTE, but also to different OFDM-based radio access technologies, like the upcoming 5G new radio. So the first and fundamental abstraction that Orion uses to do this is that of a virtual radio resource block, or VRRB. So the VRRB is the minimum allocation unit that is revealed to the control plane of a slice. And the VRBs are characterized by a capacity, which basically indicates the amount of physical resource elements that are encapsulated into them. So depending on the radio access technology that is being used, and also by the configuration of this radio access technology, different VRBs can have different capacities, but generally this is a way to show to the control plane of a slice what is the minimum allocation unit that could be used to schedule a mobile device. Now, another thing that is important to note here is that the VRBs that are revealed to different slices are mutually exclusive, which means that the physical resources that they map into are not the same, and therefore scheduling decisions that can be made from the control planes of slices are never going to have a conflict. So this allows us to reveal the minimum allocation units to control planes of slices, but this is not the only problem that we have here, because physical radio resources and their VRB counterparts cannot always be used in all combinations for the scheduling of a mobile device. There are many occasions where you might have frequency dependencies, and therefore you cannot combine the resources in any way that you want. And to give an example as to when this might happen, let's consider uplink scheduling in LTE. So in that case, a mobile device can only be allocated resources that are contiguous in the frequency dimension. So for example, if these gray blocks that you see here are resources allocated to a mobile device, this would be a valid resource allocation because they are contiguous. But this one would be an invalid resource allocation because they are not. So if we knew where exactly these resources are placed in the frequency dimension, then everything would be fine because we could know when an allocation is valid. But since we are abstracting this dimension and we are using the VRB abstraction, a control plane of a slice cannot be in a position to know whether such a thing is possible, when an allocation is valid. So we need to have a way to convey this information to the control planes of slices in order to, for them to make the correct decisions. And in Orion, this is achieved through another abstraction that we used, that of a VRB pool. So the idea is that each slice is provided by the hypervisor of Orion, one or more VRB pools in the uplink and correspondingly in the downlink. And each one of these pools contains one, but possibly more VRBs. And the control planes of slices can take these VRBs and schedule their mobile devices, but with the constraint that a mobile device can only be allocated VRBs from a single pool, which means that if you have resources that for some reason, like the one that I explained before, cannot be combined, then you would need to create different pools to put them in. So basically, going back to the previous example, these resources could not be combined together. The gray resource blocks could not be combined together for a single mobile device. So in the uplink, so if these were revealed to the control plane of a slice, we should create two pools and then put VRBs number 1 and 2 into one pool, and then VRB3 to the second one. This way, the control plane of the slice would know what is a valid allocation, so it could either use the resources from pool 1 or from pool 2 to schedule its device, but not both at the same time. So this is about the virtualization of the radio resources, but then we also, as I said before, we also need to virtualize the data plane state so that we can ensure that each slice has an isolated view of what is happening at the physical base station. So again, the hypervisor is responsible to do this, and let's see how this is done. So let's assume that we have a UE that belongs to slice number 1. So when this UE wants to connect to the network, it will need to go through the random access process at the physical base station. And once this succeeds, the hypervisor of Orion will be responsible to map this device to its appropriate slice using some kind of unique ID, like, for example, the IMSI that is stored in the SIM card of the device. Now, from that point on, the hypervisor of Orion is responsible to redirect all the data plane state of that particular UE to its corresponding control plane, and this state would involve things like the barriers that have been established for that UE, HRQ statuses, transmission queue sizes, signal quality measurements, and so on. So if another UE came in for a different slice, then again it would do the same process. It would redirect its state to that slice. And as you can see, in this way, each slice has a very different view of what is happening at the physical base station, and each slice is oblivious of the fact that other mobile devices for other slices might exist there. And correspondingly, any decisions that are made for each one of the slices in order to, regarding the modification of the state could only be applied over these UEs corresponding to the slice. So through this virtualization of the data plane state and of the radio resources, we can achieve our initial goal of having slices that are isolated, but at the same time share a common underlying physical layer. So based on that, we went ahead and implemented our design. For our implementation, we used as a basis the open air interface open source LTE platform. I'm not going to get into the details of our implementation here, but I invite you to join us in the demo session where I can show you more about the system, how it works, and how it is deployed. Using this prototype implementation, we evaluated our system, comparing it to the state of the art. For this, we considered a system called Flare, which uses the full isolation approach, and another one which is a use case implemented over the Flexron SD-RAN platform that follows the RAN sharing approach. And for that, we conducted a number of experiments in order to evaluate the performance of the system, but also we used a number of case studies through which we wanted to see what are the benefits of the system compared to others. Due to lack of time, I'm not going to present these results here. You can find more details in the paper. One thing that I wanted to present is how Orion would allow the more flexible allocation of the radio resources compared to the existing solutions. And so I'd just like to conclude by saying that Orion is a RAN slicing system that provides a lightweight and flexible virtualization solution for the RAN. Other things that we present in the paper, and I did not discuss here, is we show how Orion could be deployed in an end-to-end setting, and additionally how the design of Orion could be extended in order to allow multi-service capabilities within a slice in order to support over-the-top service providers. And some things that we would be interested in as future work is, first of all, how we could extend the design of Orion in order to provide support for functional splits, which is something very significant in the context of 5G. And another thing that would be interesting is to see how this design could be extended when we need to have multi-RAD support. So right now we assume that we have a shared physical layer, but what if we want to extend this to multiple radio access technologies? So with that, I would like to conclude my talk, and I'd be happy to answer your questions. Thank you.
Thank you.